Okay, so I'm happy to introduce the next speaker. He's David Gabai from Princeton University, and his title is Four-Dimensional Light Bulb Theorem.
Right, thank you very much. So it's a real honor and pleasure to be able to be here and speak on the occasion. Right, so it's a honor and pleasure to be able to speak at the 50th anniversary of the Journal of Differential Geometry, and I should say I'm proud of the fact that I have 8 JDG papers, and it's sort of an honor to have those papers there. And in fact, I sort of fondly remember that I was looking for a place to submit my first paper, and it's in Foliations that I noticed that Blaine Lawson was editor of JDG, and so I thought, well, maybe he would appreciate this paper. So anyway, so that worked out okay. So I want to talk about the four-dimensional light bulb theorem. But before I do, let me just mention this, which is that it's about the study of a special case of understanding two spheres in four manifolds. So here I'm working in the smooth category. And two spheres in four manifolds, it has sort of a long history. It's an incredibly fascinating subject, and it's really fundamental to four manifolds. So, I mean, at the very least, if you're just looking at two spheres in four space, I mean, it's an incredibly rich subject, which it's amazing how little is known about that. I mean, for example, there's every group that's a fundamental group of a knot in three space is the fundamental group of some two sphere in four space. And unlike three space, where that more or less determines the knot modulo some well-known things, I mean, it's far from it. For example, just a basic question is, if you have a two sphere in the four sphere, whose complement has fundamental group Z, is that two sphere just the standard sphere? And of course, one of Friedman's amazing theorems is, yes, that's true in the topological category, but in the smooth category, it's not known. And in general, in four manifold theory, if you have, say, an H cobordism between simply connected two, say, closed simply connected four manifolds, then if you look at this five-dimensional H cobordism, all the action can be put in the middle level, and you could see sort of the ascending two spheres and the descending two spheres. And of course, if you're in high dimensions, you could use the Whitney trick to disentangle them. But just understanding these spheres is really central. So right. So here's another case of, just here's a sort of, this is meant for more of a historical thing. So one of Steve Smale's early spectacular results was the classification up to regular homotopy of two spheres into Euclidean space, and for which he was able to turn the sphere inside out. And then later he developed extension of understanding K-spheres in N space, and then, Mo Hirsch, just extending his methods, so just developed this sort of general theory of immersions. But in particular, Smale asked, develop an analogous theory for embeddings. Presumably this will be quite hard. Even partial results in this direction would be interesting. So already when you're talking about embeddings, that well, I mean, as I mentioned, just fundamental group and just algebraic topology, and of course, incredibly sophisticated things are involved. So, but what about the question, this basic question of how to, under what conditions are two spheres actually isotopic? And as far as I know, there's strikingly little known in the subject. In fact, I mean, this, as far as I know, is really the only general theorem I know of that type in the subject, which is that if you have well, I'm stating this for two spheres bounding balls, but I mean their theorem is just true in all dimensions. But if you just have in 4 space a two-sphere bounding a 3-ball, again in the smooth category, then that's isotopic to the standard sphere. And the reason simply is that if it's bounding a smooth ball, then if you just look at just some point in the ball and just look at just a little neighborhood about that, then, well, of course, that's a standard sphere. But on the other hand, since this thing bounds this thing bounds the ball, then you could just smoothly isotope it to its approximately neighborhood. So it's just very close differentiably to just the standard thing. So therefore you can make it the standard thing. So questions of when are spheres isotopic is strikingly little is known. So the light bulb theorem is a condition, as you'll see in a moment, for two spheres to be isotopic. So here's the three-dimensional light bulb theorem. And the three-dimensional light bulb theorem says that if you have a knot that is just a smooth, simple closed curve in S2 cross S1, and that knot it hits the S2 just in one point transversely, then that knot should just be isotoped to the standard just vertical curve. And well, I mean, here's sort of just the main idea, which is that if you want to undo a crossing, you just slide that piece of knot all the way down to the 2-sphere. You just send it around the 2-sphere and just send it back up. So you could just undo crossings. And just after some number of crossing changes, you can see it's just a standard vertical thing. So the goal of this talk is to explain the 4-dimensional version. Oh, before I do that, why is this called the light bulb theorem? So if you have a light bulb hanging down from the ceiling and the cord is knotted up, then you can unknot the cord without moving the bulb. So, I mean, here, assuming the cord's a bit stretchy. And you can see that the region between the sphere and the ceiling, well, you should think, well, if that is, say, just, well, if the ceiling is like the boundary of a 3-ball and the bulb is the inside, then when you glue the bulb to the ceiling, then you get S2 cross S1. So that's why this is sort of really the same problem. So here's the 4-dimensional light bulb theorem, which is, well, you have S2 cross S2. And so you have this horizontal S2, S2 cross 0, and then there's the standard 0 cross S2. So the light bulb theorem says that if you have another 2-sphere, which hits the horizontal 2-sphere transversely in a point, and here you need in the same homology class as the vertical one, then in fact it's isotopic to the standard one by an isotopy keeping S2 cross 0 fixed pointwise. I should say 30 years ago, there's partial, well, results in this direction. Well, I guess Matsumoto, he proved this in the topological category. Actually, he proves something different, which is sort of more or less equivalent. And Litherland showed that there is actually a diffeomorphism that's pseudo-isotopic to the identity, whatever that is. So my goal is to explain this. So one of the challenges is how to think about S2 cross S2 in sort of a useful manner, at least for this problem. And the way we're going to think about it is, well, we have a vision, a picture of how to think about S2 cross S1. The way I think about S2 is this horizontal thing, and S1 is the vertical direction. So if we're going to look at S2 cross S2, let's keep the first S2 as S2, and the other S2, think of that as like S1 cross infinity, where you just contract the minus infinity to a point and the plus infinity to a point, right? If you just take a long cylinder and just contract the ends, well, then that's a two-sphere. So if you think about it that way, then, well, at least except for the end two spheres, you could think of that as just, a one parameter's worth of S2 cross S1s, which sort of, contract to S2s at plus or minus infinity. So here's just the restatement, which is that if we think of the standard two-sphere now as, we just call it G, because I think of it as this green two-sphere, and it's just S2 cross Y0. Y0 is just some point S1 cross 0. 0 is like the time parameter. There's G is the horizontal sphere. Then the vertical sphere intersects every S2 cross S1 in just the standard vertical arc. So the light bulb theorem says that if you have a two-sphere that just hits this green guy once transversely in the same homology class, then it's isotopically standard. So to get started, it's useful to think about what does a neighborhood of this green two-sphere look like. Of course, it's sort of obvious what to do in S2 cross S1. You just sort of thicken it up, and the natural thing is sort of to thicken it up a little bit in the time parameter too. I should have said, and should go without saying, after all, that point where our two-sphere intersects the green sphere, we should just assume it just agrees in just some tiny neighborhood with the standard sphere. So it's a little bit, agrees at this point, and a little bit in forward and backward time. But again, it's useful to find out what a neighborhood of this green sphere is. And to get a sense of that, it's worth understanding what does a neighborhood of a point in the two-sphere look like. So here is a two-sphere. Remember, a two-sphere is a cylinder with the ends contracted to a point. So here I'm thinking about there's the S1 direction, and the horizontal is the R direction, and then the plus and minus infinities are contracted to a point. So with this picture of S2, this green thing is a neighborhood of a point. So once we understand that, then we get a nice neighborhood of G. So, and the neighborhood of G is, well, okay, if we have this thing parametrized between minus infinity and plus infinity, then a neighborhood of G includes everything to the left of minus 10 and to the right of plus 10. And then from between 10 and minus 10 and 10, in those S2 cross S1 sections, just a little standard neighborhood in that S2 cross S1. So here's sort of a picture of this, is that a neighborhood of the green sphere is everything to the left, everything to the right of t is plus or bigger equal to plus or minus 10. So in particular, our sphere that we're trying to understand now looks standard when the t parameter, time parameter, is less than or equal to minus 10 or, bigger than or equal to plus 10. And for a generic slice, time slice, well, you're taking a three-dimensional slice of a sphere, so it's some one-dimensional manifold. So maybe it looks like that. So, I mean, it has multiple components. But the utility of thinking this way is now we can think in terms of Morse function, where we have, to the left, just a standard thing, and then we could just see how, with this t parameter, how the r changes. So, right. So now we just do basically standard Morse theory, where we look at the surface and we just perturb it slightly to be a Morse function. And so there's finitely many points, critical points of index 0, and which we could just assume are, say, happening at time minus 9. And then there's the critical points of index minus 1, which, well, for whatever reason, they could happen next, but, sorry, the critical points of index 1, they happen next, but for whatever reason, I just have them between, half of them at minus 6 and half of them at plus 6. And then the critical points of index 2 are at plus 9. So now, allow yourself to be slightly non-generic. What you could think of is that before time minus 9, there's just a standard vertical curve. At time minus 9, you suddenly see these, some number of disks. And then you just see these boundary circles for the times between minus 9 and minus 6. And then at minus 6, you see some bands appear. Those are like the critical points of index minus 1. And then there's bands appear at plus 6, and then disks vanish at plus 9. Now, you could just a minor variation of the theme is that, well, the standard vertical curve, I call that the core curve. And so this guy's the core curve, and it's easy to arrange that you could have these bands. One ends at the core curve, and the other ends at one of the circles. And so if there's n, like 2 circles, then there'll be 2 bands at minus 6, connecting the core circles. So between minus 6 and plus 6, actually the intersection is a connected one manifold. And then at plus 6, there's these bands, and there's just these disjoint circles that get killed at plus 9. So, right. So this is the way we're thinking about this.
I'm confused about the green stuff. That was the two states, transverse.
Sorry, the what stuff?
The green.
Oh, the green. So the green is our standard sphere. Oh, so these, I'm showing you 4 time slices. And so actually, the green is really just living at one time slice, so t equals 0. But I'm looking at, actually, I thickened it up a little bit. So looking at the regular neighborhood. So the regular neighborhood of the green at these various time slices is just a standard green, just ever so slightly thickened. So that's why these are like the S2 cross zeros, just pieces of its regular neighborhood. So again, we have disks appear at minus 8 and bands at minus 6 and then other stuff at plus 6. So, right. So now if we Oh, right. So here's something, to me, well, what if there's just no critical points whatsoever? Well, what that means is that at -9, we just start with this standard vertical curve, and then this curve is just coming out like being isotoped in S2 cross I, right? It's standard near the green. So what's left is S2 cross I. And as the time parameter changes, you have this curve just moving around S2 cross I, and then at time +9, it becomes standard again. So, you know, it should be obvious that's standard, but the only way I know how to do it is hit it with a big sledgehammer. So, and that is that if you have no critical points, then this sphere gives rise to a path, a loop in the space of embeddings of the interval into S2 cross the interval, where the endpoint's fixed. And by isotopy extension, if you have an arc that's sort of moving around, well, you could just sort of extend the space. Now, just a little technical point is that this loop in the embedding space extends to a loop in diff S2 cross I, boundary S2 cross I. And actually, the fact that you could sort of, you know, do the extension and just straighten it all the way up at the very end, actually, this is the point where I use it in the right homology class. I mean, after all, it could be in a little different class, which is the vertical one plus some number of copies of the horizontal one. And if it was in that class, then at time like +9, you'd have a S2 cross I with some like 2n rotations. But you need to sort of isotope that to the standard thing, fixing the core circle, which is a problem. So anyway, now this amazing theorem of Hatcher, he has these 17 characterizations of the Smale conjecture, and one of which is that diff S2 cross I, boundary S2 cross I is pi1 of the loop space of O3, and that in turn is pi2 of RP3, which is pi2 of S3, which is trivial. So therefore, basically you could use this contraction in the space of diff to straighten up this curve. So, right. Okay. So now we could assume that if there's no critical points, then this sphere is standard. Okay. So now let's consider what I consider to be basically the representative case, which shows like essentially the main difficulties. And in that case, we have two critical points, 2 of index 0, 2 of index 1. And if you make a slight perturbation, you could have, well, one disk appear at time, say, -9, the next disk appear at -8, and then the band that sort of associate this boundary curve appears at -6, and the next band's been pushed up in time to -5. So somehow I want to be able to cancel this critical point of index 0 with this critical point of index 1. So how do you do that? So, so first, I'd like to be able to say that right at this level, at this time -6, I could find an embedded disk bounding this curve and embedded disk bounding that curve, which is disjoint from like all the other stuff. So this disk is disjoint from everything else you see, and this disk just is disjoint from the band, everything else except for like this arc. So the question is, how do you do that? Well, I mean, abstractly, we have this picture. Here's our two little circles. Here's our band, which just goes all around S2 cross S1, crashes through here a bunch of times. And so I want to replace this disk by other disks which are disjoint from all this other stuff. So from the band's point of view, is these two disks are just hitting the band in various spots. So what we can do is is like, look at this first one and just stick your finger and just push it off the band. Well, if you push it off the band, okay, that's fine, but it hits the core curve twice. But let's not worry about that for the instant. But then that leaves room to push the next disk off, and then the next disk, and so on and so forth. So I've replaced intersections with the band with intersections with the core curve. But then, again, here's a spot where we're using, that we have this dual sphere. So we could just basically, we have this intersection here, and we have the sphere here, so we could just tube off this intersection. And so just take a copy of this green sphere, just pushed off a little bit, and just tube it off here. And with this, on this side, just tube it off in the other direction. And once we've done that, well, then we've, at least we've sort of cleaned up this spot and replaced this disk that passed through here by a different disk, but at least it's disjoint from everything. And we could just do that one by one and replace all these disks by disks disjoint from other stuff. So that enables us to sort of view time minus 6 with a differently. So we could use those disks to just basically straighten up the picture at time minus 6. So, we just straighten them up. Now, and we could do that because these disks, which I called E1 and E2, I mean, before they were where they originally, I mean, they were disjoint from things. So, but now remember that these disks, bounded these curves, and these curves, up to time minus 6, but all the way down to time minus 8 for E1, for boundary E1, and like to minus 5 and minus 9 for E2, they're, every time slice, they're just sitting there as just nice circles. So the isotopy, which takes this, this crazy picture and just straightens it up, I want that to be so just carried through, in all the various time slices, say between minus, actually, what is really 8.5 here and 5.5. So, right. Okay, so it looks like, really in good shape because this is really a much simpler picture than we really thought it was. However, we have to pay a price. And the price is that when we did this isotopy, then you remember at time minus 8, this original little disk appeared to our critical point of index 0. But when we did this sort of isotopy, then that took that disk and turned it into a mess. And this is the picture that we could very well see at time minus 8. You can see, like, here's a sphere, and here's a sphere, so this circle here is tubing to this inside sphere, and then out of this, there's a little tube that swings around to the outside sphere. So you can see the disk is a mess. And this nice straight band, if you push it down to the minus 8 level, it's crashing into this disk. Now, if by some miracle it was disjoint from the disk, then we'd be able just to do a cancellation, but it's not. So somehow we want to make this disk, this band, disjoint from, somehow isotope things to show this band is disjoint from this complicated disk. And to do that, I look at this curve C2, and I want to disentangle this curve from the tubes that are passing through it. So let's look at just a detail of that. Here's this circle C2, and we saw these tubes passing through. And, I mean, if it's, you're thinking about this, and you're thinking about this, and, it's late at night, and you say, oh, shoot, why don't we just move it off? And then you say to yourself, here's a tube, and here's a circle, and just move this a little bit into the fourth dimension and move it back. but that doesn't quite work, right? Because this circle here, I mean, sitting here at level -8, but it's, at every time, there's time slices in forward and backward time, at least, plus or minus 1. I mean, it's still there, so I just can't blithely move this off. But in fact, I can move it off using what I call the light bulb lemma. And the light bulb lemma is essentially this picture, where, where you have, just look at the top part of this picture. This is like what you might see in that timed S three-dimensional slice where you have the surface passing through vertically, and here's this tube. But if with a little bit of luck, I can find a path in the surface from this spot all the way down to where it intersects the dual sphere, and that path doesn't cross this, this stuff, then I can do, just like the three-dimensional light bulb theorem, I could just slide this guy all the way down, go around the two-sphere, and then just isotope it around the two-sphere, and then just bring it back. So this path is maybe some complicated path in the surface. It sort of goes outside the time, the T-8 level. Who knows where it goes a priori? But the point is that it's distinctly disjoint from these tubes, because these tubes were part of the disk that bounded C1, and when I just delete that disk, it's still a connected surface. So therefore, using this light bulb lemma, I really can move this guy off. So therefore, I essentially have this picture where this guy is off of this tube. So now I want to take this thing and just move it off into a little corner somewhere. And we can, because this is just, I could just like move it inside of, in this particular picture, just send it through here and up and out and just move it over. I mean, I'm simply using the fact that the union of the core plus the band plus this disk plus this two-sphere, it's connected. So I can, and this just is living in its own little spot. So I can move it anywhere I want. And where I want is right here. And, well, so if I do that, then I'm in pretty good shape, because now I can just isotope at the -8 level this complicated disk to the standard one. The point is that this band here is well, it's just a projection. This band really lives up at level -6. And I'm just putting it there to keep in mind what we need to do to cancel the critical point. But the point is, I mean, this is something we know from 3 dimensions. If you have S2 cross S1, and you just remove a little neighborhood of the S2, and you remove a little neighborhood of vertical S1, then you're just left with a 3-ball. So here's this S2, and here's this S1, and choose a little neighborhood that just contains the C2. Then what we have is a disk, a circle here, an unknot bounding a complicated disk. But disks are unique up to isotopy in a 3-ball. So therefore, I can just do an isotopy which just avoids the green, the vertical, the C2, and just take this thing and just move it to the standard thing. And there I am. So and now we're in really good shape, because there's just okay, well, now we're in good shape because this isotopy just was totally supported at the -8 level. Our band was up there at -5. So once we're finished isotoping the disk, we could just slide the band down And now we're ready to just to cancel the critical points. And so, right. So this is, this is the picture just, after canceling this critical point. So anyway, I've sort of tried to explain in this case how to cancel a critical point of index 0 and critical point of index 1. And in a similar manner, you could cancel all the critical points of index 0 with the critical points coming from the bands at -6, and the bands at +6 can cancel all the critical points of, that's critical point of index 1, cancel the critical points of index 2. So that's sort of an outline of this four-dimensional light bulb theorem. So in these last couple of minutes, just here are several applications. And one is, suppose we're in S2 cross D2, and you just have a properly embedded disk. Then the boundary of this disk is just a curve in S2 cross S1. If this curve in S2 cross S1 is isotopic to the standard vertical curve, then in fact, this disk is isotopic to the standard disk. So a disk in S2 cross S1 is standard if and only, a disk in S2 cross D2 is standard if and only if its boundary is standard. And using that, one can show that diff 0 of S2 cross D2 modulo diff 0 of B4, that's trivial. So in other words, if you have a diffeomorphism of S2 cross D2, then you can isotope it, well, an orientation-preserving diffeomorphism, then you can isotope it so that it's to the identity except within some small ball. And so the restriction of a small ball is, well, that corresponds to an element of diff B4, and sort of it's an open question whether homotopy implies isotopy for diffeomorphisms of the 4-ball that fix the boundary pointwise. So, right, and here's sort of another application, which is that if you have two smooth disks in a 4 sphere, which have the same boundary, then you can isotope one to the other, fixing the boundary pointwise. As I mentioned, the Cerf-Palais theorem said that disks are unique up to isotopy, but there you'd have to sort of somehow sweep it in and sweep it out. But you can now do this just fixing the boundary pointwise. So let me just try to put this theorem in a little different context. So in one dimension lower, that is, if you have an arc in, say, the 4 sphere, so that there's these two endpoints. And of course, S4 is simply connected, so you can homotop that arc to be just a standard straight arc between these 2 points. But as we know that for 1 complexes and 4 manifolds, homotopy implies isotopy, so which is more or less by general position. So this theorem for arcs in S4, that's just homotopy implies isotopy. This is the theorem for disks, 2 disks in S4. And now if you can promote this to 3 disks in S4, that is, if you have an embedded 3 disk, say, an embedded 3-ball whose boundary is the standard 3-ball. If you could isotope that to the standard 3-ball, fixing the boundary, well, then that would imply the 4-dimensional Schoenflies theorem. So actually, I think this is actually what I just said. If you can homotop a 3-ball to standard relative fixing pointwise, I believe is a stronger, perhaps equivalent, but I think it's actually a stronger, more difficult problem. But it certainly implies the Schoenflies problem. Anyway, thank you for your attention.
Thank you very much. Any questions?
So you're not able to say anything about the mapping class group of S2 cross D2 with this?
Well, I mean, the mapping, the mapping class group. So if diff of the ball was, I mean, if it was connected, then any diffeomorphism of S2 cross D2 would be isotopic to the identity, properly isotopic to identity.
I guess maybe I'm confused about the notation. Did you mean the mapping class groups?
No, I mean, mapping class group means, to me, means diffeomorphism modulo homotopy. So, I mean, I'm just saying if it's homotopic to the identity, then it's modulo diff before homotopic to identity implies isotopic to identity. That's what I'm claiming.
Rephrase that for S2 times D2, and if I have a non-trivial D2 bundle of the S2,
A non-trivial D2 bundle. I think I think that's also correct. Right, actually there's a stronger theorem that I didn't mention actually, which is Hatcher-free, which is that if you have two, so the light bulb theorem is a condition for a sphere to be isotopic to, say, the standard sphere in a particular space. But in general, if you have two spheres which intersect a third common two sphere exactly in a point, and those two spheres, so S1, say R1 and R2 intersects this G in a single point, and R1 and R2 are homotopic, and pi 1 of the four manifold has no two torsion, then I'm claiming that I can prove that that in that case homotopy implies isotopy.
motivation for my question, I think if I take the standard two sphere inside CP2.
Thank you for correcting this. When I think transverse sphere, it has to have trivial normal bundle. Trivial normal bundle is crucial. I mean, it's a fantastic question, which is to ask the same question for CP2. If you have, a two sphere that intersects CP2 standard in one point, is it isotopic to the standard thing and pushed off thing? And that's thank you for trivial normal bundles essential here.
Any more questions? So in some embedded program of 4 dimensions, there is this kind of positive result, but somehow other side, the gauge theory type thing has obstructions. And this has some kind of borderline problem of this kind so that you have a negative result together with positive results?
Yeah, I mean, that's a great question, which is that, I mean, as we all know, that in 4 dimensions, well, there's these spectacular, one spectacular result after the next. I mean, where for distinguishing spheres, but it's very rare, as far as I know, where to say that to give a condition where 2 spheres are actually the same, and somehow to be able to bridge that gap would just be, just to find find invariance where that nails down the isotopy class. That would be fantastic.
Any other questions? Okay, thank you for speaking again.
Thank you.